Hello, we will present our paper IM360, Large-Scale Indoor Mapping with 360 Cameras. In this project, our goal is to design an algorithm for large-scale indoor mapping using 360 cameras. The idea is to capture multiple images with a 360 camera, estimate the camera poses, and then reconstruct textured meshes. Before diving into the method, let me quickly explain the motivation. The first question is, why use a 360 camera for mapping? Conventional cameras are the standard tool for collecting images, but they come with a key limitation: they only capture a small field of view. Because a small field of view only covers limited areas, mapping usually requires long video sequences to capture everything. That's time-consuming, and it often needs mapping experts. In contrast, a 360 camera has a much larger field of view, so it can capture a wide area at once compared to a DSLR camera. This makes it possible to scan scenes more sparsely. You only need a few images since each one covers such a large field of view. That means shorter scanning times, and you don't need mapping experts to collect the data. But working with sparse views also creates challenges. With fewer images, we often lack overlap, and occlusions become more common. On top of that, indoor environments have their own issues, like large textureless regions and lots of repetitive patterns. Now, let me explain a method. Our method has three main components. First, I'll talk about our spherical structure for motion method. We work directly on the ERP images to find dense, accurate matches without losing any information. This allows us to build a much more detailed and reliable 3D structure. For dense feature matching, we use our previous method called EDM. Unlike detector-based sparse features, EDM gives us much denser correspondence, even in textureless or repetitive environments. Then, we build feature tracks using match quantization, which allows us to run the optimization. We reformulate traditional two-view epipolar constraint for normalized image coordinates and extends to unit bearing vectors. Also, we reformulate conventional bundle adjustment into spherical bundle adjustment using bearing vector and spherical projection. Then, solve BA by minimizing the reprojection error of 3D points. After the first step, we apply a cube map projection and train a neural surface reconstruction model, DEB-SDF, using multiple perspective images. This allows us to reconstruct accurate geometry. In step 3, we need a rendering method for novel view synthesis. But in sparsely scanned indoor environments, recent neural rendering methods like NeRF or Gaussian splatting don't perform well because most of them require dense view images. So instead, we chose classical texture mapping, which turns out to be a more robust solution for novel view synthesis in sparse view settings. We start by using cube map projections and their camera poses to build a texture map with text recon. But the traditional approach often produces visible seams and texture bleeding errors. To address this, we propose a new method for refining the neural texture map, which helps remove texture artifacts. We parameterize the texture map from classical text recon and use a differentiable rasterizer to render images from different viewpoints. For training, we simply compare our rendered result with the ground truth using photometric losses. Now we'll show the experimental results. To the best of our knowledge, our method is the first detector-free SFM method designed for spherical cameras. It produces more accurate camera poses and denser point clouds compared to existing approaches. Another interesting result comes from multi-floor scenarios, which are usually very challenging for visual localization because of narrow corridors and complex staircases connecting different levels. Even under these conditions, our method is able to reliably estimate camera poses, showing strong robustness. And using these poses, we can build the 3D model through the second step. Finally, let's look at the rendering results. We compare our method against classical texture mapping, Gaussian splatting, and NeRF. But in our tasks, both of these still struggle with rendering quality. Our method shows better rendering quality. Here is the conclusion. 360 cameras help us tackle challenges in large-scale indoor mapping that perspective cameras just can't solve. Research on perspective cameras is already quite mature, but it also faces some hard limits. So, developing algorithm for specialized sensors could be key to pushing mapping research further in the future.